So I'm just going to go over this again, but with a possible solution. So here's the example from Relativistics, and I'm going to normalize that because I'm not interested in the fact that there's twice as many photons here on the screen because you've got two slits. Therefore I don't need to go 2 squared, which makes it 4 times as large. So let's normalize it and just say you've got 1 photon going through. There's its smeared out energy there, which you don't see because of quantum mechanics. You only get chunks of energy, and you can't have a chunk of energy smeared out because then it could be divided into fringes. So it's got to just come from one spot. In order for it to be an indivisible chunk, it's got to come from one spot. Okay, so here's a theory. First of all, let's put the mechanics of double slit phases going around. At this point, I've chosen the first fringe, -1. If I move it, you see that the calculation changes. So let's just see what the calculation is at exactly 1. Oh, 0.9. What's the calculation at 0.9? Well, this phase is double phases. There's 2 of them, head to tail, have gone around and giving a total magnitude of 0.95. And then when you don't have a barrier between the point sources, then you just get infinite point sources all joined head to tail, so you end up with this smooth circle and curving around more and more, interfering with itself, and at the moment it's got a total magnitude of 0.85, and then so that's the envelope. That's squared, that one. But all you do is the calculation is simply take that one and that one, multiply them together, and then square it, and that gives you the probability of detecting a photon there, which is about 66%. And just to prove it, let me highlight that point. That's 66%. Okay, so what's my theory as to what happens? Well, it's Feynman's path integral. So it says that the photon takes off from a source in all directions, not infinite number of directions, and then you've got to add up all the paths it can take. So the phases that I've drawn are actually just a single path. But let's get rid of that and just say that this is the photon heading out in all directions. Here's the magnitude there of the double slit field, and then the red one is the envelope, and then you get the product of those two. So this is the overall wave function electric field. And now when you square that electric field, you actually get this. And what is that? Well, it's actually, now here we go. Feynman's path integral gives the field strength in all directions, which is a circumference. And then when the wave function is squared, that's the Born rule. The electric field, which is the summed phasor magnitude, turns into energy per unit volume according to the relativistic slide rule, with a gravitational field which has a probability of collapse. So there's the calculation. You've got your electric field squared equaling, dimensional analysis says it equals pressure, which is a Pascal, and I've got could rearrange that and say that it's the voltage of charge density in terms of electric charge, or I could, in terms of mass, it's actually time loss of mass density, or I could just call it joules per unit volume. You're all equivalent, which is what the vacuum energy is, the unit for the vacuum energy. So if the field collapses, an indivisible energy chunk, i.e. a particle, is detected, otherwise it's not detected. And who knows if it ever arrived or not. So this is sort of based on Roger Penrose's gravitational collapse idea. And if there's just a single slit, if it's detected at one of the slits, then you end up with a different pattern. Basically the same thing, except there's no double slit interference. So at the moment you can see that that's about a 73% chance of the electric field, the energy per unit volume collapsing, which is the square of that phasor, which is about 85.85. And so there's the relativistic slide rule, which this is all based on, and that's Einstein's special relativity. He came out with gamma, and then I completed that by putting in the rest of it. So it looks like he missed a few. So it's the relativistic slide rule, and so I just graphed it in Cartesian coordinates. It can also be graphed in circles, which is, I think, what's happening in quantum mechanics. But it can only be discovered using Euclidean geometry, and that's why I don't think it was ever discovered. So back to the double slit. And you can see the here's the wave theory. Let's just zoom out on that. Have a good look at it. And there it is. Oops, it's slightly off. It's 0.9. Make that exactly one wavelength. You'll see that it's spot on a constructive interference. If I make it 2 wavelengths, it'll be spot on the second fringe. Eventually it will anyway. As you zoom out, you'll see that it is. There's this sort of near field confusion